So can you see this, the slides?
Yes, sir.
Okay. Yes. Okay. Sorry for this delay, but we will now start. Okay. So did you go through my class, that recorded class from the last year, session 15? I hope most of you have gone through. Very
Yes.
important. Okay. So we discussed what is known as angular momentum. So today we'll do something and then we'll come back. We'll do something else actually. Today's class. I plan to do spin. So let us see this. So you have a circular orbit. Obviously, it's not circular because I cannot draw a circle hand. And you have an electron. There's a center revolving around nucleus. You can think. This is a charged particle essentially, which has a velocity. Sorry. It is. Is a velocity vector v. Okay. So some people are actually entering without LDAP. So I'm not going to allow you from the next class. You have to use your LDAP only. Anyways, so this is a charged particle revolving in a circular orbit. And you know that from physics that if you have a charged particle around so orbiting, doing orbiting motion, orbital motion, then what you have some magnetic moment. This is from your school physics, isn't it? The magnetic moment you generate when a charged particle is so basically electron is charged and it is revolving around the nucleus. So if it is a charged particle revolving in an orbit, so it will have something like a magnetic moment. And if you go back to your school physics, you know that the magnetic moment, of course, it has dimension as well as, sorry, it has value and direction, but you can always write it as something like current times area. You remember this? There's a current, the current amplitude, and there's the area. What is the area for a circle?
Pi r square.
Pi r square.
Okay. Just a minute. That it will be very useful later.
Sir?
Yes.
Sir, can you please put in the presentation mode so that
I can
yeah.
put, but then I have difficulty in writing.
Okay.
So I'll just make it slightly bigger. This should be fine. Yes.
Yeah. Okay.
So this is the area, pi r square. Okay. Now, what is the circumference? The circumference is twice pi r, isn't it? The perimeter of the circumference
Yes,
is
sir.
twice pi r. So it is twice pi r. So if this is the circumference, and so how many times it will revolve around this nucleus per unit time, per second? Can anyone tell me? So velocity, I know velocity is like it's displacement per unit time, isn't it? So if I divide this velocity with twice pi r, this will be what? This will give you,
Frequency.
Frequency.
as it will give you frequency, isn't it? So this is how many times per second? No. This is so many times per second the charge particle, or the charge, you can think, go around, isn't it? It is like that. So it will take 1 per second, it will make so many circles. It's like a frequency. It is a frequency. So then what will be the definite, what will be the value of I? You remember I is going to be what? Charge going per unit time. So I have to multiply this frequency with charge of electron. This fine? This is the current. This is current. Okay. This is the charge of electron, E. Are you fine with this? This is the charge. Okay. Now I go back to the definition of this mu. Then what will be the expression for mu? Mu is going to be VE twice pi r times pi r square. What is the expression then? This is going to be VE by 2, what? Pi will cancel, isn't it? Into r. Is this fine?
Yes, sir.
Now I can do one thing. I can just say, okay, 1 over, I just divide by mass, multiplied by mass. So what I'm going to get? I'm going to get E into m v r. What is mvr for a circular orbit?
Angular momentum.
Yes, so this is actually a charge times some angular momentum. Small l I'm using here. Is this fine? I can use capital L also if you want. I have no problem. So L is your angular momentum divided by, of course, twice m. Okay, I have not taken care of the direction here. So this is how it is. L is your angular momentum. Fine? Fine so far?
Yes, sir.
Yes, sir.
Now you have to remember that charge is negative. E is negative, whatever the charge is. So if the, can you see me? I hope you can see me. If the electron is revolving like this, you know the angular momentum in this direction, no? But this is the charge is negative, so the magnetic moment it generates, it will be in the opposite direction. You know from your class 11 physics, I guess. Your angular momentum is in this direction. Say if it is going like this, towards you is the direction of the angular momentum. But since the charge is negative, the direction of what is known as the magnetic moment would be in the opposite direction, down. So it is away from you. So if you take care of the fact that electron is negatively charged, then if you are very particular, then write in the vectorial notation, then it is like this. Okay, your magnetic moment is minus E by twice m times the angular momentum. So what does it mean? It basically means that if the particle has an angular momentum, then it will have a magnetic moment. And since the particle is negatively charged, the magnetic moment direction would be opposite to the direction of the angular momentum. Is this clear?
Yes, sir.
And if you take a magnitude of this, what you are going to get? You are going to get Of course, this is how it is, isn't it? And if I do quantum mechanics here, if I have a tiny magnet, which is your electron, they're like tiny. So electron is like a tiny magnet, isn't it? It's a charge revolving around nucleus. So doing quantum mechanics, so you know what this L magnitude would be? Can anyone tell me? What is this going to be?
Root LL plus 1 H.
Yeah. This is actually L into L plus 1 into H cross A square, and you have to take a square root of that, isn't it? So this is fine. This you know from your quantum mechanics, isn't it? We had discussed this. So, for example, if I have one electron for which L equal to 0, 1, then there will be 3 orientations, isn't it? For the magnetic moment. Like 3 orientation for the angular momentum. You know, because L equal to 1 means there will be 3 ml values, no? -1, 0 and +1. So accordingly, there will be 3 orientation for the magnetic moment. Now you start thinking of the electron as a tiny magnet for the time being. Is it fine? It is like a tiny magnet. Are you convinced that it is like a tiny magnet?
Yes, sir.
I'm using classical physics analogy, like a tiny magnet. Now think that we design an experiment with a beam of hydrogen atoms, okay? And you allow the hydrogen atom beam to pass through a magnetic field, maybe like this. Sorry, I think I need slightly more space. So I told you that think of the electron as a tiny magnet. So I can think this is my electron, like a tiny magnet. Can I think of like this? Of course, this is classical. This is your N, this is your S, whatever. Now, what do you expect? What will happen if this tiny magnet is passing through a magnetic field, as shown in the figure? Suggestions?
It will align itself according to the magnetic field.
It will align. But actually, that you'll try to align, but while trying to align, it will start doing something, some kind of motion. You remember that motion?
It's a circular motion.
Positional motion.
Precisional motion.
Yeah,
This is
that
a
is
motion.
called precisional motion, isn't it? So it will do some precisional motion, and then it will maybe it can, but it will not do anything else, isn't it? But precisional motion, why? Because the force acting on one side and the force acting on the other side, they will exactly balance each other, no? So as a result, it will start doing this precisional motion, isn't it? This happens when one thing I did not tell you. What is that thing, Anish or anyone else? One is like assumed. Something is assumed. What is that?
The magnetic field is inhomogeneous.
No, magnetic field is homogeneous. That is what is assumed here. This is for homogeneous magnetic field.
No, I meant to observe the
Yes. You
difference
are
between
one step ahead. Yeah. This is homogeneous. Now I design another experiment where I make the magnetic field inhomogeneous. Okay. Okay, I have a magnet like this. This is just my drawing. Now, what is going to happen to this tiny magnet? Any suggestion? This tiny magnet will show something, isn't it? Now the force will not be balanced on two ends, no?
So it will translate well also processing.
Yeah, so there will be a translational motion. It will start translating, isn't it? There's a force imbalance. And now you remember that this tiny magnet is an electron, and which follows what is known as rules of quantum mechanics. Okay? Rules of quantum mechanics. Is it clear? So what is going to happen? It is going, and if you put a screen on this side, say I put a screen here, put a screen here, then what is going to happen to this? Depending on the value of your L, which will decide the value of your magnetic moment, it will split. And in this case, what is going to happen? In this case, what is going to happen? Tell me how many, what do you expect here? How many points on the screen?
3,
Yes.
4, L equal to 1.
This is 3, not 4. This is equal to 1, no? So you'd expect 3 spots on the screen. This is fine. And this is because you're L equal to 1. There are 3 orientations. So it will split into 3 and it will make 3 spots on the screen. This is with the hydrogen atom, which is a tiny magnet. Is this clear?
Yes, sir.
But what happened that these two gentlemen, Stern and Gerlach, maybe some of you know the name, did an experiment where instead of taking hydrogen atom, they took something else. Okay, sorry, this is L equal to 1 means hydrogen atom. One thing I forgot to tell you. In the excited state, sorry, I should have said that. So it is in the p orbital. Anish. Okay, so in the p orbital.
Yes, sir.
That's why it is. But instead of taking hydrogen atom in the excited state, they did the experiment with, say, silver atom or sodium atom with actually s electron, the closed shell kind of thing, closed shell, and then electron sitting in s orbital. And even with that, even in that case, what they had found? They had found that on the screen you get 2 spots on the screen instead of 1. So in this case, L is what? L is 0. So no orbital angular momentum. L is 0, no orbital angular momentum. But still, the beam splits. And make 2 spots on the screen. On the screen. Okay. So the beam splits and it makes 2 spots on the screen. Okay. This is clear? So what does it mean? It basically means there is something intrinsic to this, even to this s electron. something intrinsic. Now, what is that something? Some kind of angular momentum, isn't it? Not orbital. But not orbital angular momentum. Is this clear, what I am saying?
Yes, sir.
Yes, sir. This should generate two different magnetic.
Yeah, so this is intrinsic even with s electron. So and this intrinsic angular momentum, this is attributed to what is known as spin. Okay, but this spin again, I reiterate that this spin has nothing to do with a tiny particle spinning on its axis. Sometimes people use that picture. That is not the correct picture. Okay, and you will see that the algebra associated with the operators for spin, they are very similar. They're exactly the same. Only thing is that spin has, for electron, there are only two spin states. And in chemistry, this is how spin is introduced in a course. So the spin is introduced as an additional postulate of quantum mechanics. But this is not the correct thing to do. Can anyone tell me what could be the better way to do it, of doing this?
So, just in the non-relativistic sense, we can modify the Schrodinger equation by putting sigma dot p instead of p, like the square of them. That would give the Pauli equation, which carries the spin information,
So ideally, ideally one should do this
which
with
is a
Dirac equation.
non-relativistic
Actually,
version of Dirac equation.
one should solve this, what is known as Dirac equation, where relativity is taken into account. And this will automatically give you spin. Okay, so you don't need to put as an additional postulate, but this is not done in chemistry course. If you take a physics quantum mechanics course, I think maybe quantum mechanics 2 in physics, they will discuss Dirac equation, where you have it is more complicated. You have to know what is known as field and other things. Has it been done, Anish? Anish, you have taken a course in physics, no?
So I think it's done in quantum mechanics 3.
3, okay, 3. So we are not going to discuss Dirac equation. Anyway, we will take this spin as an additional postulate, but you have to understand there is no classical analog, no classical counterpart, no classical picture. For spin. This is very important. Sometimes you have a picture like this. These pictures are useful, but wrong. Okay? So electron revolving around its axis clockwise, anti-clockwise. But anyway, you know there are only two spin states. Okay? And if you do quantum mechanics for electron, you'll see the magnetic moment. I had told you it is minus E by twice m times s, and then there is a factor 2 point something 00018. I don't even remember. One factor comes. I'm not explaining this factor. It comes because of experiment. You'll see. So this is a magnetic moment associated with an electron which spin. Okay, this is E by twice m. Like L, you have S sitting there, but there's a factor of 2 that comes for some reason. So this spin has two possible orientations. So like, remember that L, capital L, the quantum number was L, small l, and for LZ, what was the quantum number? I think M or ML. Okay, you remember this? I hope you remember. Similarly, for spin S, you have a quantum number S, S, and for HZ, you have a quantum number. What should I use? MS. Okay. So just like orbital angular momentum, you have spin angular momentum, you have operators for spin angular momentum. And what will be the value? The eigenvalues of this operator. Say if I have an operator like this. Sorry, I think I should put like this. This is better. Now this one will have eigenvalues s into s plus 1 times h cross. Okay, so which basically means the total angular total spin angular momentum would have value s into s plus 1 times h cross. Oh, this one is side root over. This is fine. Same, just analogy. Similarly, Sz would have value ms, but I told you that ms has only two possible values. This is one is plus half, another one is minus half. Of course, you have h cross here. What is this plus half? This is called spin up or alpha spin, and minus half is called spin down or beta spin. Okay, any problem so far? Now why only why the values are plus minus half? Can anyone tell me? And what will be the value of s? S is half. If f is half, because you know that 2 into s plus 1 gives you the number of orientation, no? And this is going to be 2 into half plus 1, which is 2. This is fine. So there are two possible orientations. Any question so far? Hello?
Yes, sir.
Any question so far?
Hello.
Yes.
Sir, just like in case of orbital angular momentum, we say that Lz is the projection of total angular momentum.
Along z axis, yes.
Yeah, along z axis. So how can we relate this to the spin?
You cannot relate. There is no classical analog. When you say that, you have some classical picture in mind. You can say this is a projection, but it has no pictorial description. There is no pictorial description of spin. This is an additional degree of freedom the subatomic particle has, electron has. Okay, so now if I write down the wave function now, what will be the wave function? of hydrogen can anyone tell me? So it is going to be psi, NLM, which is R theta phi, and then I should have a spin part. So for example, I can think this is alpha spin, or I can have another situation like NLM R theta phi. You have beta spin there. But two possibilities are there. Alpha is up, beta is down. Now this alpha also depends on some kind of coordinate. I am calling it omega, so as beta. This omega is called spin coordinate. Now can anyone tell me what is the difference between omega, fundamental difference between omega and r theta phi? Can anyone tell me?
We can define a range of values that r theta phi will take, but I think omega is just an arbitrary coordinate.
So yeah, so omega you cannot visualize omega. R theta phi you can visualize in a way, because if you have a coordinate system for r theta phi, there is no such thing coordinate system for omega. Is this clear? So this is how it is special. Okay. Now if this operator Sz operates on alpha omega, what will be the answer? Can anyone tell me?
Alpha.
Yeah, I will get, yes. It will be h cross by 2 into alpha. Isn't it?
Yes, sir. Yes.
And if Sz operates on beta, this is minus. Okay. Now if S square operates on alpha, I don't need to write omega again and again. I'm not writing it here. What will be the answer on your right? I just wrote in the last slide.
3 by
What
4
will,
h cross square.
yeah, I don't need to. You actually is going to be S
Half into
S
half plus
plus.
1. Yes.
Sorry, there is no. It's going to be S into S plus 1 h cross square into alpha. And you know that since S is half for electron, this is going to be which is half plus 1 is 3 by 2, 3 by 4. Basically it tells you the value of total angular momentum is now if S square operates on beta, what should be the answer? Not Anish, somebody else should tell me. A square operates on beta. What will the answer?
It's the same
I
value.
think it should be same.
Yeah, doesn't matter. It will be the same. And if you don't like alpha beta writing like this, I can switch over to this notation. You know this notation?
Circuit.
Kate notation. And one thing I can say that if I take alpha omega and alpha omega and integrate over omega, which is clear, don't mention the limits because it's not, it is a very abstract. What will be the answer?
1.
1.
This is 1. So same is true for beta. Okay. And if I take this one, what is going to happen? This one or this one? whatever. What is the answer? This is 0.
0.
So basically,
0.
alpha, beta, they also form an orthonormal set. So I can cast everything using Dirac's notation, no? Dirac's Braga and Crete notation. What will be this if I cast everything? Alpha is going to be 1. This is fine with you? And this one is? This fine? The way I have written? Same thing using the Dirac bracket notation. Is this clear?
Yes, sir.
Yes, sir.
Yeah. It is loosely correct, but not exactly correct, but it is good for this course, what I have done. So actually we'll do later that if I take Sx, I cannot Sy. This is, can anyone tell me what will be the answer on your right?
I tested SZ.
I expect SZ.
Yes. But one thing, that all these spin operators, one thing you must have noticed, have no explicit mathematical expressions. Did you notice that? Lz, L square, you can write in terms of r theta phi, isn't it? You remember Lz is minus IH cross del phi. But there is no such representation of Sz or a square or any operator associated with spin. Is this clear?
Sir, is this because of the coordinate system is not defined so well?
Not coordinate system is very abstract in this sense, and spin is an additional postulate, of course, in this quantum mechanics. So because of that, there is no representation of this coordinate system. There is no representation, this classical picture of spin. Because of that, there is no mathematical expression for the spin operators. But they have the same commutation relations, like the angular momentum operator. Okay. Any questions so far? I'm going to move. I'm now going to move to a different topic. We'll come back to spin next or next to next class. Spin is not over.
So, sir, we are
Yes, tell me.
Sir, in quantum mechanics, we know that for every physical observable, we should have one corresponding operator in quantum mechanics.
Yes.
So, sir, in case of spin,
The other way actually. Yeah, the same. Yeah, tell me. For spin,
yes.
there is a spin. You can observe spin, of course. In experiment, you can observe.
Yes,
like
sir.
the Stern-Gerlach, you measure two spin state, no? So those parts, those spin state, you have Sz operator.
Yes, sir. So why there is no such corresponding operator?
No, there are operators. Who said there is no corresponding operator? There are operators, but operators do not have any mathematical expression. See, what I've written.
Oh, yes. Yes, sir. Okay, sir.
You cannot write Sz using in terms of omega or any coordinate. You understand what I'm saying?
Yes, sir. Yes. Got it.
That is the point. That is the whole point. So I'll move to a topic. This is because of a request.
Sir,
Yes, tell me.
so if they are deriving the spin part from the Dirac equation, then they also don't get any mathematical expression for Sx, Sy, Sz.
Yes, you don't get, but in Dirac equation, you don't have the notion of wave function. If you do very explicitly Dirac equation, you have what is known as field. So this is beyond the scope of this course. Okay, we can discuss later. So this is not the usual framework of quantum mechanics. The relativistic quantum mechanics, and if you stretch it further, it will go to quantum field theory. Okay. So we'll just do this because this is from a request, due to a request from someone. Harmonic oscillator, has it been taught?
No, sir.
no, sir.
No, sir.
But yeah, I am not going to teach harmonic oscillator in detail, but I'm going to use what is known as there is something called ladder operator techniques, which we are going to use to deal with the problem of harmonic oscillator. We'll start in 1D. Of course, classically, you know that you have something, you have a spring. This spring has a restoring force K times X. So the potential is half K, something like X minus X naught whole square. So the force acting on the particle is minus dV dx, and this is equal to minus Kx. This is called Hooke's law. All of you should know. Of course, there is nothing called true harmonic oscillator, simple harmonic oscillator, because if you stretch it further, it will go to a regime where Hooke's law don't apply. That is the anharmonic oscillator. So in general, you have a potential like this Vx, which is given by Vx0, some equilibrium position x0, plus, can anyone tell me what should I write here? Any idea?
Del V del X x minus x0.
Yes. So I should write something like this is a Taylor expansion. So this time is going to be 0. And from here, if you interpret this as some kind of force constant, I'll get, of course, a factor of half. I get something like, and Vx0, it could be 0, depending on the choice of my origin. It is something like, this is a harmonic oscillator, isn't it? So K is the curvature or the force constant. Fine? This is a classical picture, harmonic oscillator. So now let us write down the quantum mechanics, quantum mechanics. Go to quantum mechanics, write down the Hamiltonian for the harmonic oscillator. What is the Hamiltonian? It's going to be h cross square okay. I assume x0 to be 0. This is fine. Is it fine to all of you?
Yes, sir.
So basically, I have this eigenvalue equation h operating on psi gives you E times h psi. Eigenvalue equation, also known as, there's another name to this.
Yeah, yes.
Yes. Time independent Schrodinger equation, but it is better to call it eigenvalue equation. Anyways, so far so good. So this Hamiltonian, you can also write it in a slightly different manner, like this, because you see that your K, you know this K, I think you know from classical mechanics, uh, 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 this thing you know, I guess. This you know from classical mechanics. Like this Hamiltonian can be written as,
Sir, omega is the angular frequency here.
yes, of course. You remember this? You remember this? How many of you? Because if I go to classical mechanics, you get nu equals to 1 by twice pi root over k by m, isn't it? So this basically means that twice pi mu, which is your omega, is given by k by m to the power half. And from here you get this. You remember this? I hope everybody knows. This is from classical mechanics. This is the same Hamiltonian written in terms of angular frequency. Omega is your angular frequency. Okay, angular frequency. Is this clear?
Yes, sir.
Now, after writing like this, let me define let me define an operator. I'm calling it A plus, this operator. And definition of this operator is this. Sorry, there is no pi. Twice m h cross omega this is A plus. Similarly, I define another operator A minus. I hope you understand. What is P? You know this, no?
Momentum of it.
Yeah, linear momentum operator. So A plus and A minus. Let us define this first and let us calculate this. A minus, A plus. Okay. If I calculate this, what is this going to be? This is a constant. They will combine. This will give you twice m h cross omega. What is going to happen? This into this. First term will be I square is minus 1 and then minus 1 here. So this will give you. The next term is going to be this minus and plus. So it is going to be I m omega p x. And then this term, which will be plus I m omega x p. And then the last term is this clear? The one, is it clear to all of you? This is very important, px and xp. P and x, so that's why px, and these are constant. And the next thing is x times p. These are constants. So I can actually modify this a little bit. If I modify this, what I'm going to get something like this. P square plus m square omega square x square, that will be there, minus I'm taking common, so minus I m omega divided by twice m h cross omega, and then here I have something like you can yes, so px, this is minus actually, plus x p. If I take common plus, then it will be like this. This is fine. I hope I have not done anything wrong with the sign. Please let me know. This plus minus is correct. Is this correct?
Yes, sir.
Anish, tell me yes. Now if I take this twice m inside, it's going to be 1 by h cross omega into so can anyone tell me what is this?
Hamiltonian.
Hamiltonian.
Okay. Yes, you're right. This part is nothing but your Hamiltonian, no? What about the next part? Is m omega will cancel, no? This will cancel, no? And this will give me plus I by 2. And what is this here? You have
Commute of x with p.
of course. One thing I have done wrong. You should have told me. What I have done wrong? Can anyone tell me? I took the other way. This is plus minus, isn't it? Anish?
Yes, sir, yes.
Yes. This is XP. Now, how many of you know what is XP commutator?
H cross by I.
H cross by I.
I H cross.
IH cross.
So I'll just
Sir,
put this IH cross here. Yes.
sir, how you have taken A plus and A minus? So I don't know that operator.
I just cook up this operator. I'm just cooking it up. I can always add two operators and define a new operator. No, this is like
Sir, I mean,
operator
sir,
A.
how you have taken A plus that you have defined, sir, A plus operator.
Yeah, I'm calling it A plus. I could have called it A, could have called it B. Doesn't matter. I'm just naming it A plus, A minus. We'll see why it is A plus, why it is A minus later.
No, sir,
Okay.
that expression 1 upon under root 2m h cut omega,
Yes.
that expression.
Just I cook up this operator. It will be very useful.
Okay.
It will be just very useful. Now XP is IH cross. So what is going to happen to this expression eventually? This expression is going to be, sorry, yes, and write like this, yes. Is H 1 over H cross omega into H, then I square is
-1.
minus 1. So it is minus 1 by 2 H crosses square, isn't it?
Sir, h cross cancels.
I think yeah.
Sorry, not H cross. H cross cancel. Yes, you're right. You're doing that. Okay, so half only. This is how it is. So this means I can write that Hamiltonian is given by, if I write like this, it will be H cross omega times sorry, Conmin, this is how it is. Now I'm writing the Hamiltonian in terms of these two operators, A plus and A minus. Okay, is this fine with all of you? I hope I have not done anything wrong.
Yes. Fine, sir.
So, but I can also, the order which these operators operate, very important. So similarly, one can write H as H cross omega A minus A plus minus half. You can check this yourself. One can also do that. One can also do that. You can check yourself. Okay, A minus A plus minus half. Okay, which basically means, this basically means that A minus A plus, if you explicitly do this product, it is going to be equal to, you know, that H cross by H cross omega plus half. Okay, and if this is the case, can anyone tell me what will be the value of this commutator? This is nothing but
1.
yes, A minus A plus A minus. You know that A plus A minus is this, A minus A plus is this. So this H cross, sorry, H by H cross omega will cancel. Half will add, it will give you 1. This is another relation. Okay. Any question so far? You're doing algebra mostly. I hope this is not done in this course. This A plus and A minus operator. Has it been done?
No, sir.
No, sir.
Okay.
Okay. Is this clear up to this? Then I'm going very, very slow. Going very, very slow. Now let me write down one statement that, okay, A plus operating on psi satisfies the Schrodinger's equation with energy now you have to show me this is true. How one can show this? Any suggestion? You understand the statement, no? It basically means that if A plus operates on psi, it will take this wave function to another wave function for which the eigenvalue is this, E plus H cross omega. You're getting my statement? If A plus operates on psi, it will give you a new psi. That psi new will have eigenvalue E plus H cross omega with the Hamiltonian H. Okay? Is this clear, the statement? So let me write down again. This is very important. So basically, if A plus operates on psi, it will give you something like psi new. I'm calling it psi new. Okay? And such that if the Hamiltonian operates on psi new, it will give you what does it mean? Now this statement is clear. So psi nu would have eigenvalue E plus H cross omega. Now you know harmonic oscillator. This is your, say, this state is psi 0. Next one is what?
psi 1.
Psi 1, psi 2. So basically, if A plus operates on psi 0, it will take you where? So basically, A plus operates on psi 0, it will give you what?
Psi 1.
It will give you psi 1. Similarly, if A plus operates on psi 1, it will give you psi 2. This is the statement essentially what I am making. But I have to show mathematical. The statement, I am putting the statement here. Okay? So in order to prove this mathematically, let us calculate this quantity H, because I want to know what happened to H operating on sin u. What is sin u? Is fine? If you have question, please let me know. If you have any question, please let me know. Is this fine?
Yes,
It's
sir.
not very difficult. Yes. Now let us do this. Now this is equal to, let me do it. You remember the expression for H cross omega. I am using this A plus A minus plus half. Of course, then you have. Then what is the next step? Next step is I keep this. I just multiply A plus from the right hand side because I can just include in the bracket, no? So we have half. That operates on psi. And this is equal to, now what I do, now I take A plus common from the right hand side. I take common, what is there inside? A minus A plus half psi. Is fine? Is this fine? This is essentially because H cross omega is constant. I can put like H cross omega. Then I put a third bracket. You have let me write down one more time. This is what you have, isn't it? Now remember, what is this? A minus A plus. I go back to this expression here. A minus A plus A minus equal to 1. Basically, this one is equal to is fine. This you know. You just showed because why? Because this I just showed in the last slide. So what I can do here, I can write this as A plus A minus plus 1 in place of this plus half. Is it clear to all of you? What I do, sorry. Yes, what I do, this part I am writing as this. Okay? Not a very difficult thing to follow. If you have any question, please let me know. Now, carefully look. I can write H cross omega and then what you have this plus this. You remember this H cross omega, this I can write it like this. Let me write it like this again. One more step. It is not required, but for your like this. So what is this? What is that part? You remember this part?
Hamiltonian.
Sir, Hamiltonian.
This is your H. So then if I write this like this is going to be A plus, so what I'm going to get, I'm going to get H plus, you know, this H cross omega will come inside, H cross omega operating on psi, isn't it? And what is this? This is, okay, let it, okay, I'm just doing one more step. Not required, but A plus, this is E plus H cross omega into psi, which is nothing but E plus H cross omega into, because this is a constant, doesn't matter. So I have proved the statement. So it basically tells you that, okay, if A plus operates on psi, it gives you a new wave function which has the eigenvalue with the Hamiltonian as E plus H cross omega. So it actually raises the function, isn't it? That's why it is called raising operator. Okay? Is it clear to all of you?
Yes, sir.
I think it is clear, I hope.
Yes, Akhilesh.
Yes. So similarly, one can show, if I have A minus operating on psi, it will give you psi nu, and for which, what is the can anyone guess? This is psi nu prime, say. What will be the eigen value?
Sir, E minus H nu.
E minus H cut omega.
Yeah, or H nu, doesn't matter, yes. So then what should I call this operator? It's called lowering operator. Okay? So basically the picture is, because this is psi 0, psi 1, psi 2. So if this will lower, so if psi, if it operates on psi 1, sorry, if it operates on psi 1, then what should I get?
Psi 2.
Yes, actually, yes, better to write like this. Let me see.
Oh, did you say A minus?
No, A minus is fine. They're fine, but yeah, I'm just with a constant, no? So that's why I'm being particular. So like psi 0, it is A minus, okay? So similarly, if A minus operates on psi 2, it will give you psi 1. Now can anyone tell me, if A minus operates on psi 0, what will be the answer?
I think it should not
It
operate.
will be psi 0, I think.
Psi 0 is the lowest, the ground state, no? The lowest possible state. So actually answer is 0, because it will, so this is the whole thing though, it cannot lower further, so it can take it to 0. So because there is nothing to go, nowhere to go. Okay, so psi, so that is the whole thing. The A minus operates on psi 0, gives you 0, and this is very useful, this relation. What, let us check. What is the expression for A minus? You can check your class notes twice, of course. If you have taken the class note, you have the prefactor. What you had here, you remember?
IP
plus m omega x, isn't it? This one operates on psi 0, and that gives you 0. So let us I, and this is minus IH cross ddx and this also tells you I square is minus 1, no? So this will give you H cross now this means decide dx. This is how it is, isn't it?
Minus m omega x by h cross.
0, 0. Yes, this is fine. So this will give you I can integrate so this will give you, let me write down here, fine. I can simplify it further. It will be something like psi 0, a constant will come here. It's clear?
You left out of it 2 x square by 2.
What x square by 2? Yeah.
Integration.
Yeah. After this integration, you get this 2. Yes. Okay. So this is how it is. Let me check. This is how it is, isn't it? Is this fine? Is it fine?
Yes.
How do you calculate A? Let us do it here only. How do you calculate A?
Sir, from normalization.
By normalization.
Yes. Let us calculate A. A is S square is going to be, I'm assuming A is real. Because it have to take square, so this 2 will go. Essentially, I am doing this. Okay. Sorry, not this one. This one equals to S square times this. Is fine?
Yes, sir.
So can anyone, now let me give you one standard integral. This standard integral is this. Integral is this. This is so if I do this, I get A1 equal to S square. This one will give you A is this m omega by h cross, isn't it? Alpha is. So this gives you A as so then actual psi 0 is going to be normalized one. And I think everybody knows this wave function is the ground state of harmonic oscillator. You can check. This is the ground. Ground state wave function of harmonic oscillator. So we'll stop here today. Okay. We'll do a little bit here on this next class, and then we'll come back to spin. If you have any queries, you can write in that WhatsApp group, or you can email me. So after 2-3 classes, I'll give you first assignment set. I hope you are following.
Yes, sir.
I hope you are following. If you have any queries, just let me know. So what I'm going to do now, I'm going to now stop presenting, and I'm going to stop recording. I'll send you the video, recorded video. Thank you.
Thank you, sir.